So I'm going to start the class. Okay, good morning everyone. So we will revise what we have studied in last class first. Okay, then we will move to the next topic that we are going to study today, right? So I hope all of you remember what we have studied in last class. Tell me, we studied about the bond model, right? How the atoms of semiconductor, the atoms of semiconductor are bonded, right? So basically they are bonded in a crystal lattice, just like diamond. Okay, now when we talk about silicon, the case of silicon, so we have discussed the case of silicon, right? So silicon have, tell me, 4 electrons in outermost orbit, and it is bonded by covalent bond, right? So this is the bond model. Now when we talk about the energy level, so I can say that in case of silicon we have 5 energy levels, right? Okay, 5 energy levels, one for 1s, then 2s, 2p, 3s, 3p. We have 5 energy levels. Okay, right, everyone? Because we know that every atomic orbit will have different energy level. Now, when we talk about the outermost orbit, so outermost orbit is 3s and 3p, right? Basically, it's third orbit. So in case of silicon, right, we have 4 electrons in outermost orbit. So this 4 electrons is responsible for formation of bond. Okay, it is responsible for formation of bond. So when we talk about the energy level of these four, I hope all of you remember this diagram, right? So when we see at any distance, or basically when we talk about an isolated atom, so we can see that, okay, we have 5 different energy levels, 1s, 2s, 2p, 3s, 3p. We have 5 different energy levels, right? In which each electron is filled. So in 1s, we have 2 electron filled, okay, out of 2 positions. In 2s, 2 electrons filled out of 2 positions. In 2p, 6 electrons filled out of 6 positions, right? Same with 3s and 3p. Okay. Now, if I'm talking about isolated atom. Now, if I'm having 1 mole of atom, suppose if I'm having 1 mole of atom, right? Or I'm having 1 centimeter cube of silicon, then what will happen, right? So in that case, there will be lots of silicon atoms which will be close to each other, right? So they'll be close to each other, okay? And because of that, the internuclear distance decreases, okay? The internuclear distance decreases, and due to the decrease in internuclear distance, okay? So I can say that the energy level will not be same anymore. Why? Because according to Pauli's exclusion principle, my voice is not breaking, Manoj. I don't think that my voice should break, right? Because my internet is very good. Okay, till the time I'm in Bangalore, I won't be having any issue with my internet. Okay, so it's your internet which might be having some issues, right? Okay, so yeah, I was saying that yes, so as we decrease the internuclear distance, the atoms of silicon will come closer, and they will affect the energy level of each and every atomic orbital, right, everyone? So instead of having a single energy level, the energy level of all those electrons, all those electrons will split, right? It will split. Okay, and yes, so after splitting, right, instead of having one line, we can see a band, right? We can see a band, but since it is a continuous process, it's not like, okay, till one moment we have a single line, right? Then after some time, it will split into 10 to power 3 or 10 to power 23 lines. It won't happen, right? It will split in a continuous fashion. Okay, so there will be some distance at which it starts splitting, right? And there will be some distance at which it is totally splitted. Okay, and obviously the temperature is also one of the factor here. So I've considered 4 lines, right? One line is the distance at which it started splitting. The second line at which the energy level of 3p and 3s, okay, the energy level of 3p and 3s merged together, right? We cannot further identify the difference in energy between 3s and 3p. And then this is a third line in which there is a vacant band, right? There's a vacant band. Okay, this is a region in which there's no energy line. I'm not talking about the electrons, I'm talking about just the energy lines. Okay, so now beyond this point, your 4n states, where n is basically a number of atoms, right? 4n states is basically divided into, sorry, total is 8n, right? 6n plus 2n, 8n states is divided into 4n states each, right? 4n electrons each. Okay, now this line is the line that I'm considering for study. Okay, so I can say that, okay, since we know that electron will try to achieve lowest energy state, so we have 4 electrons, 4n electrons, so all those 4 electrons will come in the lower energy band, right everyone? Okay, and the upper energy band will have no electrons, it will be empty. So I can say that the low energy band is called as valence band and the upper energy band is conduction band. And the gap between these two energies, right, the gap between the topmost energy band, energy level of valence band and the bottommost level of conduction band is called as energy gap, right everyone? Right? Okay, so this is what we have studied in last class. Okay, so then after this we studied what is intrinsic semiconductors. Okay, so when we talk about intrinsic semiconductors, this is the bond model. Now when we talk about this bond model, we have 4 electrons of silicon and each electron is bonded using covalent bond. We have this conduction band, we have this valence band, and there's energy gap, right? Energy gap. Now this is intrinsic semiconductor. Now as the temperature increased, okay, this is at 0 Kelvin. This is at 0 Kelvin. Okay, so nothing is going to happen at 0 Kelvin. But suppose we increase the temperature. What happens? Tell me. Now, when we start increasing temperature, the molecule will start vibrating, it gains some energy, right? And yes, the bond breaks and this electron will be free. This electron will become free, right everyone? Okay, so I can say that the electrons start moving from valence band to conduction band because they will get enough energy, right, to overcome this energy band, right? Okay. Okay, so I can say that we have free electrons in conduction band. So we will have free electrons in conduction band. Okay, we will have free electrons in conduction band, right? Free electrons in conduction band. And now, because this electron is leaving its position, it is creating an empty space, right? It is creating an empty space here, right everyone? Okay, and this empty space will also move. Why? Because suppose we talk about another electron of another silicon, right? So it will try to occupy this position and then this empty space, which we call as hole, will move. Okay, so I can say that we have two kind of movement over here, right? One, the movement of electron, and second, the movement of holes, right? What is holes? Holes is the empty space which is created due to the, tell me, removal of electron. So number of electrons will be in conduction band and number of holes will be in valence band. Okay, now we studied that number of electrons in conduction band is equal to number of holes in, tell me, valence band, and this is equal to Ni, which is number of intrinsic particles. Now I hope all of you know what is number of intrinsic particle, right? So basically it is the number of charge carriers. Okay, you can just say that it is number of charge carriers, right? Now the relationship that we have studied, right, which should be followed in both extrinsic and intrinsic is N into P is equal to Ni square, right? So this is the relationship which is being followed, right, between, yes, number of holes and number of electrons, free electrons. Okay, right? Now see, if someone wants to study more, right, so I've included some slides which have some mathematical or more equations. Okay, so I guess all of you understood this. So this was the thermal equilibrium, which I talked about, that if we increase the temperature, right, what will happen? Will it keep shifting to, will the electron keep shifting from valence band to conduction band, right? No, it doesn't happen like that, because at certain temperature, after some certain temperature, the reverse process will start, right? The reverse process will start, and the electrons at this conduction band will recombine with your holes, right? Okay, that's why that will be your equilibrium. Okay, so that is the case when you keep on increasing temperature. Okay, it's not that all the holes, sorry, all the free electrons, all the electrons will shift to conduction band. Okay, now if you see this, now this is for some people who like might feel interested in the equations. As I told you that it is not as simple as we know. Okay, there's lots of math involved. Okay, so just to give you idea, this is the expression that we study. This is the only expression that we study, right? Okay, but if you refer some books, okay, or some advanced materials, right, so you will get the idea that number of electrons is given by NC, which is the density of electrons in conduction band, right? This is the density of conduction electron in conduction band, e to the minus EC minus EF by KT. I hope all of you know what is EF. EF is the Fermi energy level, which is energy level in between this, right? There will be one level which is in between the conduction band and valence band, right? Okay, so this is your Fermi band, energy of Fermi level, right? Okay, so this is the equation. Now, if you don't have to remember this equation, just try to relate this equation. Don't you think that this equation is something like the equation that we have already studied in chemistry? Tell me, do you think that it is something like that? K is equal to K naught e to minus E upon RT, something like that, right? Right? So yes, so obviously I'm not, yeah, Arrhenius equation, something like that, right? But I'm not going deep down into this equation, right? Just for your idea how this equation will hold true even for extrinsic semiconductors. I told you in last class that for you just consider that this will hold true, right? So I just wrote this equation to let you know why it will hold true. Okay, or what is the equation of Ni? So when you talk about Ni, see, this is a big equation of Ni, right? If you see, this is a big equation of Ni. So you don't have to worry about this equation. You just have to think the terms. So it is t to the power 3 by 2. I'll show you another simple equation. Okay, it is t to the power 3 by 2, then some constant, and e to the power minus eg by 2t. eg by 2t. Now eg is your difference between this conduction band and valence band. Okay, so I can say that the number of intrinsic charge carriers depends on three factors, right? Obviously, it depends on temperature, it depends on material also, because this constant comes from material, right? And depends on the energy gap, right, everyone? This is what we need to know. That's it. That's it. Okay. So this is the simplified expression for Ni. This is the simplified expression for Ni. So you might see this in advanced chapter test or advanced major test or any advanced tests. Okay, so this is the expression for intrinsic semiconductor, right? If you recombine all the constants, we have A, then it is T to the power 3 by 2 and E to the minus Eg by 2 kT. So if you want to remember, you can just remember this equation. So you know that, okay, A and Eg both depends on the material, right? T is a factor which is depending on temperature, right? Okay, so the some examples that we have taken away here for germanium, for silicon, and for silicon semiconductors made up of both gallium and K is Boltzmann constant, na? Right? We have studied Boltzmann constant, right? In chemistry, which is R by Na, right? Okay, so K is Boltzmann constant here. So see how Ni is changing, Ni is changing. Yes, obviously T should be in Kelvin. That is like by default, whenever we have T, it should be in Kelvin. Okay. So now I hope everything is clear to you guys. Tell me. Okay. Okay. Then the next thing that we studied is N-type semiconductors, right? We studied N-type semiconductors. So in N-type semiconductors, I think, see, the thing is I just picked this because I was horrible at drawing figures. So I just used the made one. Okay. So this is not my handwriting. My handwriting is horrible. This I just picked this from one lecture that I follow, or I used to follow in my college days. So now when we talk about N-type semiconductor, when I talk about N-type semiconductor, okay, yes, so N-type is not traveling, pentavalent. Remember this, N-type pentavalent, because the number of electron is more, right? Just remember, N-type number of electron is more, N-type negative, right? Even though it's neutral, you can remember N-type negative like that, okay, right? So N-type is pentavalent. So when we talk about intrinsic semiconductors, intrinsic silicon, this is the this whole, right, is the case of intrinsic semiconductor, intrinsic silicon, right, in which at 0 Kelvin we have just valence band and sorry, conduction band and valence band. At T is equal to T1 Kelvin, the electron will be excited and it will, some electrons will move, right, creating number of free electrons as well as holes. This is about intrinsic. But when we talk about intrinsic, when we dope it, right, just dope it with arsenic. Okay, suppose I dope it with arsenic. I hope this is clear. Tell me guys, this is clear. You can just keep your phone in landscape mode and you can see this, right, everyone? All of you can see this, right? Because it is clear from my side. Okay, if you cannot see that, so it might be your internet issue. Okay, because it is clear from my side. Okay, so yeah, so I said that, okay, if I'm adding one impurity, which is arsenic over here, right? So only 4 electrons of arsenic will be involved in bonding with silicon, right, everyone? Right? So only 4 electrons of arsenic will be involved in bonding. So what about this 1 electron? So this 1 electron, right, at 0 Kelvin, okay, at 0 Kelvin, it will be with arsenic, right? Obviously, it will be with arsenic. It won't leave the atomic orbital of arsenic. But what will happen? What will happen when you give some temperature, right? Now, when you give some temperature, okay, when you give some temperature, this electron will move into free electrons, yes or no? Tell me, yes or no? Okay, now what will happen to energy band? Let's see. Let's see. Now we know that this electron is not involved in bonding, right, everyone? This electron is not involved in bonding. Okay, so for this electron, there must be, or you can just say that it is almost, right, almost closer to my conduction band, right? This electron, the energy level of this electron, right? This extra electron is almost close to conduction band, right? Okay, but below conduction band, because still it has some electrons now. Yes or no? Tell me, right? So this energy level is due to the electrons of donor atom, okay, which is bit below this conduction band, and this energy is almost around 3 kT. Okay, it is almost around 3 kT, right? Right, everyone? Okay, now this is at T is equal to 0 Kelvin. What will happen? What will happen, right? If we increase the temperature, tell me what will happen if we increase the temperature? So obviously, whatever was happening in intrinsic semiconductor, intrinsic silicon, that will happen, right? Some electrons will move from valence band to conduction band. Just energy, right? This is just the energy difference between this level and the conduction level, right? This is almost equal to 3 kT, almost equal to 3 kT, right? This energy level, this energy level. Okay, yes. So Now, what do you think? We have electrons, right? We have free electrons at this level, which is the level just below this. So obviously this electron will freely move into conduction band, right? This electron will freely move into conduction band because the energy required is very less as compared to this electron. Yes or no? Yes or no? Right? Okay. Now, yes. So, and this will become, this AS will become positive charge. This AL will become positive charge. Okay. Right? Now, what can we say about the charge carriers? What can we say about the charge carriers in this case? I can say that, okay, I'm having more number of free electrons now. I'm having more number of free electrons now in conduction band, right? In conduction band, okay? And in valence band, okay, valence band, the number of holes will be less only. So I can say that in this case, number of free electrons is much, much greater than number of, tell me, holes. Right? Holes. Okay. And the difference in the energy level, EC minus ED, right? The EC minus ED. Here I have written almost 3 kT. Now, in terms of electron volt, it is around 0.5 to 0.45 electron volts, right? It is different for different material. So it is around 0.5 to 0.4 electron volts in terms of electron volts. Right, everyone? Concept clear? Right? Okay, and Nd is the number of donor atom. Nd is the number of donor atom. Okay, right? Nd is the number of donor atom, or basically it's the density. Yes, yes, doping means adding different element. Okay, right? So I hope all of you understood what is p-type semiconductor. Okay, now when we talk about n-type, when we talk about n-type semiconductor, that was n-type semiconductor. Now when we talk about p-type semiconductor, if you see the p-type semiconductor, right, ED is the level, na, ED of the energy level of dopant or donor atom. Got it, Prashant? Okay, now let's see the p-type. So for intrinsic, it is same, right? For p-type, I'm having one acceptor atom, which is trivalent, right? Trivalent, one acceptor atom. Now, when we talk about acceptor atom, right? So we have a vacant position, right, everyone? We have a vacant position over here because it has only 3 electrons, right? And silicon need 4 electrons. Okay, now I can say that, okay, this vacant position have some energy level, and the energy level of this vacant position will be a bit more than that of your valence band. Yes or no? A bit more than that of your valence band. Right, everyone? Right? Agree? Okay, now what happens now? Now, because it is vacant, one electron from other silicon will occupy this space, right? Okay, and it leads to creation of more holes. It leads to creation of one holes. But if you see this electron which is moving, it is not moving to, this is not moving to conduction band. This is moving to this energy level, which is the energy level of acceptor. This is the energy level of acceptor. Yes or no? Right? This is the energy level of vacant atomic orbital of acceptor, right? So I can say that the electrons, right, now the electrons which is shifting, right, are going to this energy level, which is EA, okay, and it leads to generation of more holes, right? Got it, everyone? So I can say that in this case, number of holes will be much, much greater than number of electrons, free electrons, right, everyone? Anyone have any issue in this? Prashant, you understood this now? See, some will move, obviously some will move. Just think about it, na? Just think about it, right? Just think about it. Harsha, Prashant, right? Think about it. One level is without electron and one level is with electron, right? Okay, if this level is without electron, what do you think? It will be below this valence band, right? Below this energy level or above this energy level? Think about it. If the energy level of acceptor will be below the energy level of valence band. Electron will be moving in this now, right? Right? But obviously, right? Initially, electrons is in valence band, right? Okay, right? Naturally, it is in valence band. Naturally, it is in valence band. Okay, after giving the electron, then it will move now. That's why it should be above valence band. Got it, Harsha? Prashant got this? Okay, right? Okay, so this is the equation that I was trying to show in last class. I just said that for your sake, for your syllabus, you just have to remember. You just have to remember that this n into p is equal to ni square follows for both extrinsic and intrinsic, and this is the derivation. This is the derivation how it follows for both extrinsic and intrinsic, right? So you don't have to worry about this. You don't have to worry about this. You just have to know that yes, this relation holds true for both extrinsic and intrinsic. Okay, right, everyone? Okay, okay. So again, this is the derivation, right? Yes, yes. Who said that n is equal to p? It is just saying that if you increase the number of dopant, right? If you increase the number of dopant, right? If the number of n will increase, the number of p will decrease, and it will happen in such a way that the product is constant, right? The product is ni square. That's what it says. Okay. If you want to know more, so this slide will explain more what happens actually, what is the total number of electrons, what is the total number of holes. But I guess you need not to have you don't have this in your syllabus, so it's fine. So these things you don't have in your syllabus. Okay, so I just want to explain this. What will happen? What will happen to Fermi level, right? Or what will happen to this level? Okay, when electron is added and when holes are more. So see, this is Fermi level. You just have to remember this. You just have to remember this. Okay, just have to remember this. Fermi level, right? Okay, suppose I'm having two Fermi level, EF1 and EF2. EF1 and EF2. So it is clearly visible that EF1 is close to EC, right, everyone? Which is conduction band, and EF2 is close to valence band, right? So if I say the difference between conduction band, right, to Fermi level 1 and conduction band to Fermi level 2, right? Okay, is like this, means the difference between the Fermi energy level. Yes, it will be a standard value. Okay, you just have to know that there's something like this. You don't have to know deep into that. Okay, even though you don't need to know these things, but I'm just explaining you to have this idea that doping, right? When doping occurs, when number of electron increases, then the Fermi level will shift in which direction, because there will be some problems on this in your module, right? That's why I'm explaining this. Okay. So as I said, now we know that if we have two Fermi levels, if we have two energy levels, two Fermi energy levels, EF1 and EF2, where this distance is certainly less than this distance. So I can say that EC minus EF1, which is difference between conduction band and Fermi level band, right, is less than EC minus EF2, right? Now, I can use this relationship because this is the relationship for N. If you remember, N is equal to NC, e to the power minus EC minus EF by KT, right? So the inequality will change because of this negative sign, and I can say that N1 is greater than N2. What does this say? What does this say? Right? In which case, number of electrons will be more in case of Fermi level 1 or Fermi level 2? Tell me. Tell me, guys. It is just a level, Harsha. It is just a level, right? It is just the level. Okay. Or I can just say in inverse. I can just say in inverse. If the number of electron increases, okay, can I say that if the number of electron increases, okay, the Fermi level will shift. The Fermi level will shift toward conduction band. Tell me, if number of electron increases, the Fermi level will shift toward conduction band, right? Okay, and vice versa, if number of holes increases, it will shift toward valence band. This is the statement that you have to remember. Okay, so if this is the statement that you have to remember, if number of electrons will increase and number of protons, sorry, holes will decrease, right? Fermi level will shift toward conduction band and vice versa. Okay, so this is only the thing that you have to remember, just this concept. Okay, right everyone, right? Because you'll be asked just this concept, you won't be asked about these things. Okay, at least not in mains. And this is the derivation again of that, so I'll be skipping this. Okay, what is the meaning of more than one and less than one? It is just the level, right? It is just a level in which there will be some energy. Okay, it is just a level in which there will be some energy, right everyone? Okay, so I hope all of you have understood the concept that we studied in last class. Tell me yes or no, right? So we revised whatever we have studied in last class. Okay, okay then. So we will move to the next topic, which is PN junction, right? What is PN junction? What is diode and all those things? Okay, everyone. Don't worry, I'll make a nice PPT. Right? I'll include all the concepts. Okay, right? I'll include all the concepts and share it with you guys. Okay. Okay. So this relationship that we have studied, right, which is Ne into Nh is equal to Ni square, is called as mass action law. Okay, this relationship that we have studied, Ni into Nh, is called as mass action law. This holds true for both extrinsic as well as intrinsic semiconductors. I hope all of you understood this concept now. Okay. And before moving to next topic, let's try to solve some problems. Okay. Before moving to next topic, let's try to solve some problems. Okay, let's try to solve this problem, guys. Tell me, let's try to solve this problem. Everyone, try to solve this problem. Everyone should try, guys. Everyone should try. This is just formula putting and getting, just formula putting and getting. And we have already studied these concepts, especially for question number A, okay, in modern physics, right? Photoelectric effect, or even in atomic structure, that energy is equal to, tell me, hc by lambda, an electron volt, it will be 12400 by lambda, because the value of Hc in electron volt is 12004. Very good, Prashant. Very good. Correct. Right? Yes. So A is correct. It is just formula putting getting. Right, everyone? So A is easy, which is Hc by lambda. Lambda is given. Right? So lambda is given in nanometer. Okay. Now what about B? B is also easy. E by kT you can calculate, right? K, the value of K is what? R by Na. So I'll just give you the value of K. Everyone, I'll just give you the value of K. It's just calculation. I just wanted to, right? I hope all of you can solve this. Okay. Right, everyone? Very basic. Now, next question. Try to solve this question. Everyone, try to solve this question. A p-type semiconductor has acceptor level 57 milli-electron volt above the valence band, right? Now, I hope everything is clear, right? What is the meaning of this? What is the maximum wavelength of light required to create a hole? Tell me, guys. Tell me. So this is the mix of semiconductor as well as your modern physics. Milli-electron volt, na? Milli-electron volt. How can it will be mega? Mega is capital M. Manoj, seriously, small m is always milli, na? When we have studied small m as mega? Yes, very good, right? Vishnu, calculate, it won't be, and you have to, yeah, you have to tell me what is a unit. What is a unit? Yes, Prashant, correct, very good, correct. Guys, see, even though this is an easy problem, calculator will not be allowed, right? So this might become a difficult problem unless until you know how to do the approximation, okay? Right? So the answer is correct. It is 21.7 minus, sorry, 10.7 angstrom versus nanometer or this, okay? Next, next. Tell me guys, this one, third one. Very good, Samik, correct. This one, third one. Try to solve this. Tell me guys. Okay, I'm muted. Sorry. Since when I'm muted? I don't remember. I was muted for long or what? Okay. So question number third, I explained question number third. Did you hear that? No. I just explained question number third. Okay. Okay then. So I'll try to explain once again. Okay. I didn't know that I was muted. Okay. So question number third, right? What is given? You just have to understand the problem, right? The question given is one indium atom, right? One indium atom will be there for every 500 power 7 silicon atoms. Unitary method, right? Okay. So one indium atom for 500 power 7 silicon atom. Indium atom 1 by 500 power 7, right? Now for 500 power 28 silicon atoms, how many indium will be there? 500 power 28 by 500 power 7. Got it? Just unitary method, nothing more than that, right? So 10 to the power 28, 21 atom per meter cube is the number of indium, right? Which is the acceptor atom over here, right? And then convert into centimeter cube, right, everyone? Okay. Now question 4, it is basic formula putting getting. How did you make mistake? Okay, question number 4, formula putting getting, right? Everyone got this? It is Ni square, na? Prashant, Swamik, Radhika, Gauri, Himashri, Shrishti, Shreya, everyone is getting? And one more thing, yeah, who is the, I guess, Vishnu and Abhin attend all the classes, right? Vishnu attend all the classes, I guess. Vishnu just post the name of students who are absent in the group itself. Okay, right after the class, just post the name of students who are absent in group itself. Okay. Okay, Vishnu. Every day for every class, not for this class, for every class. Okay. Except for biology, obviously you cannot do anything about biology. For biology, I'll ask someone else. Okay, Ashisha take attendance. Very good. Because see, when I teach, I don't focus on who are present, who are absent, right? So it's better just tell me who are absent at the end of the class and message in the group itself. Okay. Yeah, I know that. Okay. Okay. Right. So this is it. So I hope all of you understood. Now, there's one very small concept, right? Very small concept which I've covered, right? I just assume that you guys know about resistivity, conductivity, current density, and all those things. Tell me, just tell me, do you know these things? Because I won't be spending much time on this if you already know. Okay. Right? What is current density? What is resistivity? What is mobility? Because I will be using these terms in Pn junction, right? When we talk about drift current, right? Or diffusion current, I'll be using these parameters. So anyone who do not know anything about this, please let me know. But I hope that all of you have studied these things, current electricity, right? Current density, yes. Okay, very good. Okay. Now, yes, so when we talk about some conduction in semiconductors, so we should know conduction occurs because of what, right? Because in conductors, it occurs because of free electrons, right, everyone? It occurs because of free electron. There is no doubt in that. Okay, right? But in case of semiconductors, we have two different tell me two different charge carriers, right? Okay, which is holes as well as free electrons. Okay, so when I talk about total charge density, okay, total charge density, I hope everyone remember this. Charge density is NeVd or basically any, right? Any VD, everyone remember it's not where VD is drift velocity, okay, which is mu e. Okay, now when we talk about electron, this is just one charge carriers. But when we talk about yes, intrinsic semiconductor, we have both electrons as well as holes. We have both electrons as well as holes. Okay, so the drift velocity for both electrons and holes will be different, right, everyone? The drift velocity of both electrons and holes might be different. Okay, and charge would be same because it's just charge of one electron. Doesn't matter if it's positive or negative, right? It charge would be same. So I can say that for semiconductors, especially the intrinsic semiconductors, right? The charge density, total current density, sorry, the total current density will be due to free electrons as well as holes. Okay, right, everyone? Okay, and mobility will be the net sum of mobility of both electrons and holes. So conductivity will also be given as En mu e plus mu h. Everyone is getting this very simple concept because we will be using these formulas, right? Okay, right? Now, when we talk about p-type, we know that for p-type, number of holes is much greater than number of electrons. So I can just ignore this. Yes or no? I can just ignore this. Harsha, this is the velocity of electron which is moving from conduction this valence band to conduction band, and this is the basically the number of holes or the movement of holes in valence band only. Okay, that's why the basic concept, right? They are guys. What is hole? Tell me, what is hole? Hole is nothing, right? Hole is nothing. It is empty space. When I talk about the movement of hole, it is actually the electron which is moving. It's not that it is a positive charge and negative charge, right? That you're saying, okay, positive charge will move this, negative charge will move this. It's not like that, right? It is just an empty space, right? An electron is moving, only electron is moving, right? And empty space is created over here, right? Do not consider this as positive charge and negative charge. It is not this. It is empty space and negative charge, right? So when negative charge is moving, then it creates empty space over here, right? You have to know what is the basic difference between proton and holes. Proton and holes are not same, right? Protons are positively charged particles where hole is just empty space. Got it? Harsha, Manoj, got this? Okay. Okay. So we will just ignore this. Anyone have any issue in this? Tell me, right? I hope all of you understood this. Okay, so we will be using this formula, direct formula. Okay, we'll be using these formulas. Okay, okay. Now, if we have mixed impurities, then obviously it will be mixed due to both sigma E and as well as sigma H, right? If we have mixed impurities. Okay, now let's solve this problem. Let's solve this problem number 6, everyone. Solve problem number 6. Everyone should solve problem number 6. Why there's a dot over here? This is 480, guys. I don't know why there's a dot over here. Okay, so try solving question number 6. Everyone, try solving question number 6. Just count the number of people minus 2 because like 2 account will be of mine, right? And just see, just take the screenshot and see who is absent, who is present. As simple as that. Okay. So 28 students are present today. 28 students were present. Were present yesterday also. Just try solving this, guys. See, n is ni. Here n is ni, okay, which is number of intrinsic particle, right? Okay. Question number 6, formula putting getting. Okay, so I hope all of you can understand this simple formula, right? Sigma is equal to, you have to find what conductance, right? Sigma. Sigma is this one, right? It is your, tell me, different, and mu n and mu p is given differently, right? Mu n and mu p is given, means mu n is mu e, mu p is mu h, right? Yes, Kalpana, very good, right? Very good. So Ni is given electron hole pair. Ni is number of intrinsic charge particles, is number of electron hole pair. Yes or no? Okay. So there you made a small mistake with there, calculation mistake. Just check, right? You just have to multiply this. Ni is given. Okay. E we know, which is charge of electron, which is 1.600 minus 19, right? Yes, Prashant. Okay. Very good. Correct. Now try solving this question. Try solving question 7. See, these are very basic questions, right? Very basic questions, but it is just the information. If you don't know what is the meaning of whole electron pair. Yes, chemistry, correct. Now question number 7, everyone, try solving question number 7. So Prashant, Manoj, Samik, I hope all of you understood what is Ni now, right? Okay. Question number 7, guys. Very good, Vishnu, correct. It is formula putting getting, right? Okay, NH is given, NH is given, Ni is given, okay? Because this is Ni, right? Okay. So the answer is 5 into 10 to the power 9. Okay, formula putting getting. Chemistry, check your calculation. Okay, now there's one more problem. Just see this. You don't have to solve. There's one more problem over here, right? Now this is also basic formula putting getting. You have to identify which type of semiconductor it is, and then you have to calculate number of holes or number of electrons. So these are the type of questions which can be asked based on mass action law, right? Okay, mass action law. What is mass action law? It is, right? Okay, then we will start PN junction now. Right, everyone? Ready? We will start PN junction now. Okay. So what is PN junction? Let's try to understand what is PN junction. Okay. So yes. So if you keep one PN semiconductor, one P semiconductor, one N semiconductor, and if you just keep it all together, right? Will it become PN junction? No, right? It won't become. right? You have to have a same crystal, right? Same crystal which consists of both. Okay, that's why, see, if you see the diagram over here, I cannot say that this is your PN junction, right? I cannot say that this is a PN junction, okay? Because we just have two different type of semiconductors kept one one above other, right? Okay. Now, they are different kind of PN junctions. There are different kind of PN junctions, right? The first is alloy method or alloy junctions, in which, right, we form a kind of alloy of both P and N type of semiconductor. So if you see the third diagram, right, I hope you can see the third diagram, right? So here we have a small junction, which is basically the intersection, right, of both P type and N type. Okay, right? Okay. Then the second is we have diffusion type and then vapor deposit. So again, this is just a theory. You just have to know, okay, this is this type. I'm not going to this theory type. Okay, I'll just explain what is PN junction, right? This is the different type of methods in which you can create PN junction. Okay. Okay, everyone. Don't worry, I'll share each and every notes with you. Now let's see how this PN junction works. How this PN junction works. Let's see this first. Okay, right? Now, suppose I'm having this, yeah, first of all, we don't have this battery. Suppose I'm just having this P type and N type. I'm just having this P type and N type. Okay. And this is your boundary of separation. I'll consider this as boundary of separation. Okay. Right, this is the final figure, right? I'll just explain you. Wait, I'll just explain you what happens. Okay, suppose I'm having this PN junction. Okay, a PN junction like this. Okay, so here I'm having this line. Okay, now this side I'm having P type, and this side I'm having N type. This is not connected with any battery for now. Okay, so suppose this is my atoms. Okay, my atoms of p-type semiconductor, and this is just the dopants. I'm just showing the dopants. Okay, I'm not showing the silicon atom. I'm just showing the dopants. Okay, right? Now this is your N type. Now tell me, when you talk about the dopants are basically your trivalent or pentavalent, yes or no, right? Trivalent or pentavalent atoms. Now after losing electron or after gaining electron, they will have some charges, right? They will have some charges. So I can say that, okay, now I can say that this, right, this dopant. So I'm just showing the dopants, okay? So this dopant will have what charge? Tell me, this dopant will have what charge? It is p-type, right? P-type. Think about it, guys, right? That's a mistake you guys are doing. Since it is trivalent, it will take one electron, yes or no? Think about it, yes or no? Since it is, right, see this, Anna, it will take one electron. Now, after taking electron, it becomes negatively charged, right? So the dopants of p-type are negatively charged. Negatively charged. Okay, got it. Tell me. No, I'm just talking about P and N, Prashant. I'm not talking about anything. I'm just talking about P and N, right? Okay, I'm not talking about the junctions. I'm just talking about P, right? Individually taken dopant of P, right? When it takes 1 electron of silicon, it takes extra electron, so it becomes negatively charged. And when we talk about the charge of donor atom of N, it will become positively charged. Okay, step by step, right, everyone? Okay, now, so I can say that when we talk about p-type, we have lots and lots of holes, because if the electron is accepted by this, so we have lots of holes, right? I'll just draw holes. So I'll draw holes like dot. So these dots are holes. Yes or no? Tell me. We have lots of holes in case of p-type, right? And in case of, yes, and in case of n-type, what do we have? In case of n-type, what do we have? Electrons. Yes, very good. I'll just select this. This, okay. So we have electrons. So electrons. So can I say that, okay, p-type is like the bed of donor and silicon, right? And the electron cloud of, or the clouds of holes, right? And n-type is, right, bed of donor atom and silicon and cloud of electron. Okay, right? Or you can just imagine the scenario in which we have this thing. Okay, so this is the scenario. I hope all of you understood this. Now, what do you think? What will happen if we talk about this junction? If there's no boundary, if there's no boundary now, right? I remove this boundary. Okay, I remove this boundary now. What will happen? Tell me. If I remove this boundary, what will happen? Positive charges are donor atoms, na Harsha, right? Positive charges are donor atoms, because donor atoms, after giving the electron, become positive charge, na, right? So yes, right? Now think intuitively what will happen, right? There's some counterintuitive argument also, but right, these electrons will try to fill these holes. Yes or no? These electrons will try to fill these holes. So I can say that, right? Just go by layer. The first layer of the first frontmost electrons will fill the holes, right? Will fill the holes. Okay. So I'll just remove everything. Okay. I'll remove this. So first layer of electrons. Okay. I'll remove everything. Okay. I'll remove everything for now. So first layer of electrons, donor atoms will be there. Okay. Obviously donor atoms will be there. I'll draw donor atoms later. First layer of electron will remove first layer of holes. Make sense? Yes or no? Tell me, make sense? It's not just one layer. There may be multiple layers. I'm just giving you example. In the same way, second layer of electrons may recombine, and second layer of holes, right, may vanish. Got it? Right? Got it? So I can say that, okay, let's hold. So we have this region, okay, this region. Now, obviously, in this region, we do have donor atoms and acceptor atoms. We do have donor atoms and acceptor atoms. Okay, we do have donor atom and acceptor atom. But because of recombination, these atoms are exposed now. Yes or no? These atoms are exposed now. in this region. So I just call this region as region X, right? In this region X, right? Since holes and electrons are recombined, right? Now it is not neutral anymore, because when you talk about this, right? Negative and holes, they are neutral almost, and this is neutral almost, right? But this is not neutral anymore, right? We have exposed layer of negatively charged acceptor atoms and positively charged donor atoms, right? Right, everyone? So tell me, what will happen? This electron, this negative charge will repel further electrons, yes or no? Will repel the further electrons to recombine, okay? Or if you just think about it, okay, right? No, Manoj, they are atoms. How can they become neutral, right? It is your phosphorus and someone is your boron, right? How can they become neutral? They won't combine and form a compound, right? Okay, so I can say that we have an electric field in this direction, yes or no? Because positive charge, negative charge, obviously it will be electric field in this direction, right, everyone? Right? And this electric field will prevent the movement of holes and electrons. Anyone have any issue? Tell me, anyone have any issue till this point? Everything is clear till this point? Okay, now let's see. So I can say that this whole PN junction, this whole arrangement is divided into three sections. 1, 2, 3. One section, right? P type, pure P type. Now this is your region where there is no holes or electrons. So this is called as depletion region. This is called as depletion region. Right? Region where electrons and holes will recombine. Okay. Prashant, just think about it. What is P type? What is P type? You accept, you use boron for P type, yes or no? Tell me. We use boron as a donor, sorry, as a dopant in P type, yes or no? Tell me. And what boron will do? Boron will accept one electron. Boron will accept one electron, yes or no? Right? After accepting one electron, what will become? It will become B minus, yes or no? Right? So now you got your answer. Now you got your answer. Tell me, Prashant. Okay. And same thing happened with N type. Okay. Now let's see some potential, right? Let's see the potential. Okay. So I can say that, okay, from this point to this point, suppose it has some potential which will be constant, right? Suppose it has a potential which is like this. Like this. Now, what do you think? In this depletion region, right? There's electric field, yes or no? Yes or no? And we know that V is equal to what? V is equal to, tell me, E into L. Right? E into L. Any issue in this? Tell me, any issue in this? And positive charges here, negative charges here. Potential will be more at where? At positive charge side or negative charge side? Tell me. Right? So since there is electric field, right, we will have potential difference and it will increase, right? It will increase like this. Okay, it won't be that slant, right? like this. Okay. Then again, after this, we have this N type. So again, potential will be constant. Understood, everyone? So this is potential. This is potential. Potential. So I can say that. Okay. Okay. When we talk about the potential, right? Between this is P type, this is N type. We have this difference, right, of potential delta V, right? Got it? Okay, this is called as barrier potential. Barrier potential. And this is different for different atoms. For silicon, it is almost 0.7 volt. Okay, got it, everyone? Means what does it mean? It means electron should have, or electron should cross this much potential to cross from one junction to other junction. Now, everyone understood what is PN junction? Tell me, everyone understood what is PN junction? Prashant, there is no electric field, na? Tell me, there is no electric field in P type or in N type. Harsha, they move randomly. They don't move in a specific direction, right? And when holes and electrons are moving, right? They're moving randomly, okay? So there's no fixed direction. We have, yes, we have electric field only in depletion region, okay? Right? Unless until we connect something, unless until we connect a battery or something like that, right? Okay, so I've explained all the things. Where V is constant, V is changing in depletion region. No, that's what I said. I said before and after depletion region. Okay, Prashant, right? I said before and after means it is constant here, it is constant in this point, and it is constant in this point, right? It is changing in this point, right? It is changing over here. Now, see, it is changing over here. Okay, and this is called as barrier potential. Okay, got it, everyone? Tell me, got this? Everyone got this? Okay, very good. Okay, so if you see, if you observe this, right? Okay, what is happening over here? If some electron, suppose some electron, right, go from this side to this side. Okay, some electrons move from this side to this side. There's movement of electron, right, from N type to P type, N type to P type, movement of electron. Yes or no, right? That is your diffusion. That is your diffusion, right? This is, I'm just talking about diffusion. Okay, and due to this electric field, there will be electric field, right? Electric field. Electron will have force in this direction, in opposite direction. Yes or no? Yes or no? Tell me. Tell me, guys, yes or no? Yes. So it might happen that some of these boundary electrons, some of this electron will be shifted in this direction. Okay. Right. Okay. Okay, everyone. Right. Okay. So we'll move to our next topic. I hope all of you understood till this point. Okay. Let's move to our next topic, which is diffusion and drift current. But before that, right, we have studied the width of depletion region is very small, right? Potential barrier, I've already told you for silicon it is 0.7. Okay, and for germanium it is 0.3. The next is diffusion and drift current. Now let's see what is diffusion and drift current. Okay, so see, first of all, drift current is due to electric field. Okay, that's one thing you have to remember. Drift current is due to electric field. Okay, if there's no electric field, then there's no drift current. Understood? Mostly it will be given, Harsha, but for silicon and germanium, it's better to remember. Okay, right? So I'm saying that we have two types of currents as we have discussed: drift current and diffusion current. And drift current is always due to electric field. Means if there is no electric field, we won't be discussing about drift current. Understood? Yes or no? Tell me, guys. Okay. Okay. Now I'm not talking about PN junction. I'm just talking about a normal conductor. I'm just talking about one type of semiconductors, right? Now, suppose I'm having one side positive charge, one side negative charge. I hope all of you can see this. Guys, can you see this? Is it clear? Right? I'll keep on explaining. So if you don't get anything, please let me know. So I can say that here we have positive charge and here we have negative charge, right? Positive charge and negative charge. Now, what do you think? What would be the direction of electric field? The direction of electric field will be from positive to negative. Yes. Yes. This is what we have already studied in electric current. Okay, so I'm just revising it. Now, if electric field is in this direction, is in direction of positive to negative, the force on electrons will be in opposite direction, right? The force on electrons will be in opposite direction. It will be from this side to this side, okay, right? And force on holes, or basically the holes, I'm just considering holes as positive charge particles, right? Because we have to consider holes also, right? I'm just considering hole as positive charge particle. I'm considering hole as P. Okay, hole will be in the direction of electric field. Okay, because unlike conductor, in case of semiconductor, we have two charge carriers, both electrons as well as holes. So we have to consider the current due to both holes as well as current, right, everyone? Any issues? So when you talk about electrons, we have charge minus Q, force will be minus QE. Holes, since holes is empty, vacant, right? It is the movement of electron. Then again, if one electron is leaving, again it creates a hole. Okay, sorry guys, my laptop was like hand. Okay. So yeah, so I hope all of you can relate this now. Tell me, all of you can relate this now. So JDiff, Prashant, right? What is happening? Electron is moving, right? Electron is moving. It's not that nothing is happening. Okay. Now think about it. We have a hole over here. We have a hole over here, an electron over here, right? Now, if